Our galaxy is hiding secrets in plain sight. The familiar band of the Milky Way, which arches across our night sky, is not a serene cosmic river. It is a vault of mysteries, a home to objects so bizarre they rewrite the rules of physics as we know them. This is a journey to 25 of the strangest things astronomers have ever found right here in our own galactic neighborhood. By the end, you will see our cosmic home not as a quiet suburb, but as an arena of titanic explosions, invisible forces, and ancient ghosts. We will encounter a region of space so empty it defies logic, and a gravitational monster that pulls entire galaxies toward an unseen fate. What you believe is the most surprising thing a galaxy can hide. Our story begins with a pull we cannot feel, a silent river in space dragging everything we know toward an unseen shore. This is the first great mystery, the Great Attractor. Picture the universe not as a static collection of galaxies, but as a vast flowing current. Every galaxy near us, including our own Milky Way, is caught in this current, moving at an astonishing speed of over 600 kilometers per second. We are not drifting aimlessly. We are being pulled with immense purpose toward a specific point in the sky, toward the constellations of Hydra and Centaurus. But when astronomers point their most powerful telescopes in that direction, they see a frustrating wall. It is called the zone of avoidance, the thick, dusty plane of our own galaxy's spiral disk. This dust blocks our visible light view, hiding the source of this cosmic tug of war behind a perpetual galactic fog. So what could possibly possess the gravitational strength to reel in entire galaxies? Early theories suggested a previously unknown supercluster of galaxies, a gathering of matter so vast it could command such motion. But as observations with X-ray and infrared telescopes began to pierce the dust, a more complex picture emerged. They found not just one dense cluster, but an even larger flow, suggesting the Great Attractor might itself be moving, pulled toward something else far more massive in the distance. So this first strange object is a paradox. It is a destination that is also a waypoint, a gravitational landmark we are desperately trying to see, hidden in the blind spot of our own cosmic home. That colossal pull toward the unseen is a reminder of the immense forces at work in our galaxy's violent heart. And from that very center, another mystery erupts, not pulling matter in, but violently blowing it out. The Fermi Bubbles are two colossal spheres of searing energy, ballooning above and below the galactic plane. They form a faint, ghostly hourglass that spans half the width of the Milky Way itself, each lobe stretching an incredible 25,000 light-years into the emptiness. You could fit our entire solar system inside one of these structures thousands of times over and still have room to spare. We only discovered them in 2010, not by seeing their faint glow with our eyes, but by mapping the sky with the Fermi Gamma Ray Space Telescope, which detects the universe's most energetic light. What it revealed was a pair of symmetrical, bubble-shaped regions flooding space with gamma rays, a clear sign of particles moving at nearly the speed of light. So what created this pair of cosmic lungs, exhaling a furious wind for millions of years? The prime suspect sits at the very base of these bubbles, the supermassive black hole known as Sagittarius, a star. Astronomers theorize that millions of years ago, our galaxy's dormant heart awoke in a spectacular tantrum. It may have briefly transformed into a brilliant quasar as a massive cloud of gas and dust fell into its clutches. The black hole, unable to consume all that matter at once, channeled the excess energy into two opposing jets, inflating these gigantic bubbles with ultra-fast particles. It was a brief but catastrophic eruption that has left a permanent scar on our galaxy's sky. Not everyone is convinced by the black hole outburst theory, however. Some suggest the bubbles could be the cumulative shockwave from hundreds of generations of massive stars being born and dying in a frenzy at the galactic center, their combined stellar winds and supernova explosions blowing this immense structure. Yet the perfect symmetry and sheer scale point to a single, focused event, a titanic burp from a sleeping giant that reminds us our galactic core is not nearly as quiet as it seems today. The echoes of that ancient galactic eruption may still be whispering to us today, not in the form of vast bubbles, but as a faint, enigmatic glow. Deep within the crowded core of the Milky Way, astronomers have detected a persistent and puzzling signal known as the galactic center giga-electronvolt excess. It is a diffuse haze of gamma-ray light, the most energetic form of light in the universe, concentrated right where our supermassive black hole resides. This is not the violent flash of a single explosion, but a steady, soft luminosity that permeates the central region. The mystery lies not in its presence, but in its specific energy signature and its shape. This glow peaks at an energy level of around 1 giga-electronvolt, which is like a specific color on a violent, invisible spectrum. When scientists tried to explain it using all the usual cosmic suspects, the math simply did not work. The glow is too smooth and too spherical. It does not match the expected pattern from known populations of rapidly spinning neutron stars called pulsars, which would appear as distinct pinpoint sources. It also does not align perfectly with the gamma rays produced when cosmic rays slam into clouds of gas. So what is creating this persistent, energetic fog at the heart of our galaxy? One of the most thrilling possibilities involves the universe's greatest missing piece, dark matter. Theorists suggest that if dark matter is made of certain types of hypothetical particles, like WIMP, weakly interacting massive particles, they could be concentrated in the galaxy's dense core. There, in a slow, silent process spanning eons, these particles might occasionally collide and annihilate each other, converting their mass directly into energy and producing a spray of gamma rays at precisely the energy we observe. It is a beautiful idea that the shadowy substance holding galaxies together might finally reveal itself through a faint, deadly light in our own backyard. Yet, extraordinary claims require extraordinary evidence, and the scientific debate is fierce. Many researchers are diligently searching for a more conventional astrophysical explanation, perhaps an undiscovered population of very faint, fast-spinning pulsars, or some novel form of cosmic ray interaction we do not yet understand. The hunt is on to decipher this cryptic signal, a glow that could be the mundane exhaust of forgotten stellar engines, or the first, faint signature of the universe's hidden architecture. This faint glow of potential dark matter annihilation is a ghostly signature of the galaxy's most elusive substance, but to build the stars we see, the universe requires something far more tangible, a cosmic lumberyard of raw material. Drifting through the spiral arms of the Milky Way is an object of almost incomprehensible scale and simplicity, a thread of pure potential named the Maggie filament. Discovered just a few years ago, this is not a star, a planet, or a nebula. It is a colossal river of cold, atomic hydrogen gas, the most basic building block in the universe. Stretching for an astonishing 3,900 light-years, it is one of the largest coherent structures of its kind ever identified within our galaxy. To grasp that distance, if you could travel at the speed of light, it would take you nearly 4 millennia just to go from one end of this gaseous thread to the other. It snakes through the galactic disk, a dark and frigid highway in space. What makes Maggie so profoundly important is its state. This vast reservoir of hydrogen is largely undisturbed, quiet, and cold. It represents the universe in its most fundamental creative mode, holding the pristine material from which future stars and solar systems will one day be born. Astronomers believe filaments like Maggie are the skeletal framework of the galaxy, the hidden scaffolding upon which the glittering jewels of spiral arms are hung. They are the delivery system, channeling raw gas across vast distances until gravity triggers its collapse into dense knots that ignite as new suns. Finding and studying Maggie is like discovering a blueprint for galactic construction. By mapping its length, its density, and its motion, scientists can finally see how the Milky Way organizes its star-forming fuel on the grandest of scales. It answers a fundamental question: where does a galaxy keep its spare parts? The answer is in these dark, winding rivers, flowing silently in the spaces between the stars, waiting for the signal to begin building anew. While Maggie represents a slow, patient flow of creation, other objects in the Milky Way tell a story of violent, chaotic expulsion. These are the runaway stars, stellar projectiles rocketing through the galaxy at speeds that defy imagination. One of the most spectacular examples is Zeta Ophiuchi, a brilliant blue giant that is not drifting peacefully through space but fleeing. It is plowing through the interstellar medium at a breathtaking velocity of around 87,000 kilometers per hour. You can see the evidence of its frantic journey not in the star itself, but in what lies ahead of it. As Zeta Ophiuchi races through thin clouds of gas and dust, it acts like a cosmic speedboat on a still lake. The star emits a powerful stellar wind, a constant stream of charged particles flowing from its surface. This wind slams into the interstellar material directly in the star's path, compressing and heating it into a brilliant, glowing arc called a bow shock. In telescopic images, this appears as a dramatic, crescent-shaped wall of red and blue light, a permanent sonic boom made visible, announcing the star's reckless passage. But how does a star, born in a relatively stable nursery, get catapulted into such a frenzied solo voyage? Astronomers have identified two primary cosmic catapults. The first and most dramatic mechanism involves a supernova explosion in a binary star system. Picture two massive stars locked in a mutual orbit. One of them reaches the end of its life and detonates in a cataclysmic supernova. If the explosion is slightly lopsided, it can kick the surviving companion star clear across the galaxy, like a stone from a slingshot, sending it careening into the void with immense speed. The second mechanism takes place in the dense, crowded core of a star cluster. Here, stars are like billiard balls in a cosmic pool game, constantly nudging each other with their gravity. Through a complex series of close gravitational encounters, a star can be flung out of the cluster entirely, gaining enough velocity to escape its gravitational home forever. Famous examples like Mu Columbi and Ae Aurigae are believed to be such cluster ejections, their trajectories traced back to a single point of origin millions of years ago. The fate of these stellar fugitives is a lonely one. They will continue their high-speed journeys, eventually leaving the spiral arms of the Milky Way behind to travel through the desolate galactic halo. They will never form planetary systems, as their speed would strip away any protoplanetary disk. They are destined to live and die as solitary travelers. Their brilliant light and dramatic bow shocks the only testament to the violent events that set them free. They are the galaxy's castaways, born from chaos and condemned to an eternal sprint through the darkness. The fate of those runaway stars is written in light and stellar wind, but some of the galaxy's strangest stories are told in a language we cannot see at all. They are written in radio waves, and they describe shapes of perfect, bewildering geometry. Scattered across the cosmos, astronomers have begun cataloging a new class of phantom, the odd radio circles, or ORCs. These are enormous, faint rings that appear only in the radio portion of the electromagnetic spectrum, invisible to optical, X-ray, and infrared telescopes. They are so perfectly circular they look like cosmic smoke rings, some so vast they could encircle entire galaxies, while the most famous ORCs discovered so far lie far beyond the Milky Way. Their existence raises a haunting question. Could similar, unexplained ring-like structures be hiding within our own galaxy, camouflaged against the noisy radio background of the galactic plane? The search is already on, because if such an object existed nearby, it would present an unparalleled mystery right on our cosmic doorstep. Their appearance is deceptively simple. In radio telescope data, an ORC is just that, a crisp, hollow circle of enhanced radio emission. There is often no visible object at its center, no obvious source of the energy that created this perfect form. It is as if a titanic, spherical shockwave expanded through space and then froze, leaving only its circular edge glowing faintly in radio light. The scale is mind-bending, with some ORCs spanning hundreds of thousands of light-years across, making them among the largest single structures ever observed. The fact that they are only visible in radio waves suggests they are made of extremely high-energy electrons spiraling in magnetic fields, a phenomenon called synchrotron radiation. But what event could create such a vast, symmetrical, and isolated shell of these particles? The theories proposed to explain them are as extraordinary as the objects themselves. One leading idea is that they are the aftermath of a cataclysmic event at a galaxy's center, perhaps a past eruption of a supermassive black hole so powerful it sent a spherical tsunami of energy blowing out in all directions. Another possibility is that they are the remnant of a colossal merger between two galaxies, the final, fading shockwave from that violent union echoing through intergalactic space. More speculative and far more thrilling is the notion that these perfect circles could be the throats of theoretical wormholes, or perhaps the imprint of a war in a distant civilization, the remnant of a technology so advanced it leaves a galactic-sized scar. What makes ORCs so compelling to scientists is their complete novelty. They do not fit neatly into any known category of astronomical object. They are a new puzzle, a shape that should not exist according to our old maps of the cosmos, forcing radio astronomers to redraw their charts of the possible. Finding one within the Milky Way would transform this puzzle from a distant curiosity into an immediate and intimate enigma, a perfect circle drawn in invisible ink across our own starry sky. This hunt for invisible shapes in our own sky leads us to a place where the absence of everything is the strangest feature of all. We must venture beyond the Milky Way's spiral arms to confront a true cosmic anomaly, the Boötes Void. To call it a void is an understatement. It is a staggering spherical region of near-nothingness, a bubble in the fabric of the cosmos so vast it could contain thousands of galaxies like our own, yet it holds almost none. Its diameter is an almost incomprehensible 330 million light-years. If you placed our Milky Way at the center of this void, you would look out in every direction and see a sky of profound, unbroken blackness. The nearest major galaxy would be so far away its light would be a faint, lonely smudge, taking tens of millions of years to reach you. This is not merely an empty patch, it is a galactic desert on a scale that defies our understanding of how the universe arranges itself. According to our best models of cosmic evolution, the distribution of matter after the Big Bang should have created a universe with a relatively even, frothy structure like a sponge. Galaxies and clusters should be separated by modest voids, but nothing on the scale of the Boötes Void. Its existence is a deep puzzle. How could a region this large end up with so little matter? One theory suggests it might be the result of many smaller voids merging together over billions of years, like soap bubbles coalescing into one gigantic cavity. Another, more speculative idea posits that it could be the imprint of an encounter with a parallel universe in the distant past, a scar from a collision with another reality. While that remains in the realm of hypothesis, the sheer physical experience of being inside the void is a thought experiment in profound isolation. With no nearby stars to illuminate the night, your home galaxy, the Milky Way, would stretch across the heavens as a breathtaking, solitary ribbon of light. You would have a front row seat to its grand spiral structure, but the rest of the cosmos would appear to have vanished. The constellations we know, the distant glow of neighboring galaxies like Andromeda, all would be absent. It would be a universe of one, a single island of stars in an ocean of darkness so deep it challenges our very notion of a populated cosmos. the Boötes void stands as a silent reminder that the universe is not just defined by what is there, but by what is startlingly, inexplicably not. That profound emptiness of the Boötes void is a monument to what the universe lacks, but back within the rich, dusty heart of our own galaxy, astronomers have just discovered stars that are doing something entirely new, something that adds to the cosmic inventory in a strange and smoky way. After decades of scanning the skies, we thought we had seen every kind of stellar behavior, from serene burning to violent explosions. We were wrong. Nestled in the crowded stellar nurseries near the galactic center, a hidden population of elderly stars has been caught in the act of a bizarre, slow-motion eruption. Astronomers have named them the Old Smokers. These are not brilliant, hot young stars. They are ancient red giants, stars in their final act, having exhausted the hydrogen fuel in their cores. For most of their long lives, they were quiet and unremarkable, fading slowly into obscurity. But then, something extraordinary happens. Over a period of months or even years, an old smoker will begin to dim dramatically, sometimes fading by as much as 97%, almost vanishing from view. This is not because the star itself is dying out. Instead, it is belching out colossal clouds of fresh, dark dust. Imagine a cosmic volcano, not of lava, but of soot and complex molecules, erupting in a slow, sustained plume that shrouds the star from our sight. This behavior was a complete and total surprise. For years, the dimming events were noted in survey data and often dismissed as glitches or data errors, or perhaps just mundane eclipses by orbiting dust clouds. It was only through persistent, long-term infrared monitoring that the truth emerged. The stars themselves were the source of the smoke. They were manufacturing vast quantities of dust in their outer atmospheres and then coughing it out into space in episodic, gigantic fits. The importance of this discovery cannot be overstated. These old stars are cosmic chemists, and their smoky eruptions are a primary delivery mechanism for heavy elements. Throughout their lives, red giants forge elements like carbon, oxygen, and iron through nuclear fusion in their cores. In their final, smoky phase, they seem to be finding a way to expel this enriched material not in a single supernova blast, but in a series of slower, more deliberate exhalations. This dust, rich in complex compounds, eventually mixes with the interstellar medium, becoming the raw material for future generations of stars, planets, and perhaps even the building blocks of life. The very soot that hides these stars is the fertile soil from which new solar systems will grow. But what triggers this strange volcanic behavior in a star's old age? The mechanism remains a tantalizing mystery. One leading theory points to intense magnetic activity. As these giant stars rotate and churn, their magnetic fields could become twisted and powerful, acting like a giant stirrer in their extended atmospheres. This could dredge up material from deeper layers, cool it, and condense it into solid dust grains right there above the surface, until the buildup becomes so great it is blown away in a dusty wind. Another possibility involves pulsations and instabilities inherent to this late life phase. The outer layers of a red giant are incredibly extended and tenuously held by gravity. It might only take a slight internal shudder, a thermal pulse from a shell of burning helium, to loft vast quantities of gas to a height where it can cool and condense into this obscuring smoke. Whatever the cause, the old smokers have rewritten the final chapter for a whole class of stars. They show us that a star's death is not always a quick, brilliant supernova or a quiet fade to a white dwarf. For some, it is a long, smoky retirement, a series of fitful breaths that seed the galaxy with the elements of creation, all while hiding their final, productive acts behind a self-made veil of cosmic dust. If the old smokers are the galaxy's slow, dusty exhalations, then the cannonball pulsar is its most violent, precise sneeze. Discovered hurtling through the void at a speed that defies belief, this neutron star is a cosmic bullet. Its official name is PSRJ0002 plus 6216, but astronomers gave it a far more fitting nickname. It is moving at over 1,000 kilometers per second, a velocity so immense it could travel the distance from Earth to the Moon in a mere 6 minutes. But the true spectacle is not just the pulsar itself, it is the colossal trail it leaves behind, stretching for 13 light-years, a distance that dwarfs our entire local stellar neighborhood, is a brilliant, narrow tail of energized matter. This tail glows in X-rays and radio waves, a permanent contrail of a star moving too fast for its own good. It is the aftermath of a shock wave, the pulsar plowing through the thin gas of interstellar space like a speedboat through a calm sea, compressing and heating the material into a luminous wake that points backward like a cosmic arrow. That arrow points directly to the scene of the crime. By tracing the pulsar's path backward across the sky, astronomers found it leads with uncanny precision to the center of a supernova remnant called CTB1. This expanding shell of gas, located about 10,000 light-years away in the constellation Cassiopeia, is the debris field from a colossal stellar explosion that occurred roughly 10,000 years ago. The geometry is perfect, inescapable evidence. The cannonball pulsar is the surviving, ultra-dense core of the star that exploded, and it was shot out of that explosion with such ferocious, lopsided force that it is now fleeing the wreckage at breakneck speed. This makes it one of the clearest and most dramatic examples of a supernova acting as a cosmic catapult. The physics behind this stellar slingshot is both violent and elegant. When a massive star reaches the end of its life and its core collapses, the resulting supernova explosion is rarely perfectly symmetrical. If more material is ejected in one direction than another, or if neutrinos stream out unevenly, the conservation of momentum dictates a recoil. The remaining neutron star gets a tremendous kick in the opposite direction, launching it into a solitary, high-velocity journey across the galaxy. In the case of the cannonball, the kick was so powerful it has already escaped the confines of its own supernova bubble. It is a runaway remnant, a tombstone racing away from its own grave. This single object provides a textbook case study for understanding one of the galaxy's great recycling and dispersal mechanisms. Supernova are not just brilliant explosions that forge heavy elements, they are also engines of stellar propulsion. They can launch their dense, city-sized remnants on trajectories that will eventually carry them out of the galactic disk entirely. The cannonball pulsar, with its unmistakable tail and clear origin point, is a gift to astrophysicists. It allows them to measure the speed, trace the lineage, and calibrate the immense forces involved in a star's death throes. It is a natural laboratory for studying kick physics, demonstrating that a dying star can impart more energy to its leftover core than is required to escape the gravitational pull of the entire Milky Way. Where will this cosmic cannonball end up? Given its current velocity, it is destined to eventually break free from the galaxy's gravitational grasp. It will become an intergalactic traveler, a lonely, spinning beacon of dead star matter sailing through the vast, empty spaces between galaxies, its brilliant tail fading as it leaves the galaxy's gas behind. It serves as a permanent reminder that a star's death is not an end, but a transformation, and sometimes that transformation involves being fired from a celestial cannon. The violence of stellar explosions gives way to a profound and active silence in our next object. Near the brilliant stars of the Southern Cross lies a patch of the sky that seems to be missing, a deep black void known as the Coalsack Nebula. For centuries, observers navigating by the southern stars saw this dark blotch not as an object, but as an absence, a literal hole in the fabric of the heavens where no stars shone through. The truth revealed by modern astronomy is far more fascinating. The Coalsack is not an empty hole. It is a towering, frigid cloud of gas and dust so incredibly dense that it completely blocks the light from the hundreds of thousands of stars that lie behind it. It is a cosmic curtain drawn across a portion of the Milky Way, creating the illusion of nothingness. If you could fly a spaceship into this cloud, you would find yourself enveloped in a darkness deeper than any earthly night, where the dust grains are so thick they would blot out the galaxy itself. This darkness, however, is not a dead zone. It is a stellar nursery in its earliest, most secretive stage of construction. Inside those opaque, freezing depths, gravity is slowly at work. Minute particles of silicate and carbon ice are sticking together, and vast reservoirs of molecular hydrogen are collapsing under their own weight. Within these dark cocoons, protostars are simmering, gathering mass and heat, hidden from our view by the very material that is giving them birth. The coal sack represents the universe in its incubation phase. It challenges our instinct to equate light with activity and darkness with emptiness. Here, the most fundamental act of cosmic creation, the birth of a sun, begins in total obscurity. It will be hundreds of thousands, perhaps millions, of years before nuclear fusion ignites in those hidden cores and the fierce stellar winds from the new stars begin to blow away their dusty shrouds. Only then will the coal sack's secret labors be revealed as the dark nebula transforms, giving way to a brilliant new cluster of stars that will finally illuminate the very cloud that once concealed them. This object teaches us that the greatest acts of cosmic genesis often happen behind closed doors, in the dark, quiet places we mistakenly call voids. The darkness of stellar nurseries gives way to an even deeper architectural mystery at the very heart of our galaxy. Our Milky Way is not a simple, smooth spiral. Its core is a dense, brilliant bulge of ancient stars, and for years, astronomers assumed this central region was shaped like a flattened football, a structure called a classical bulge formed long ago by violent galactic mergers. But our galaxy had a secret shape hidden within that light. When scientists meticulously mapped the distribution of millions of red giant stars using infrared surveys like WISE, which can see through the galactic dust, a startling pattern emerged. The bulge is not a smooth oval. It is distinctly boxy, and when viewed from the side, the stars within it trace out a clear, though faint, X shape. It is as if someone took two vast stellar wings and crossed them through the galactic center, a signature embedded in the positions of billions of suns. This is not what you would expect from a calm, orderly galaxy. That X shape is a profound clue, a fossil record of a dynamic and relatively peaceful history. The leading explanation is a story of internal evolution, not catastrophic collision. Our Milky Way possesses a strong central bar, a dense straight line of stars cutting through the core. Think of this bar not as a rigid structure, but as a fluid, rotating entity. Over hundreds of millions of years, the gravitational forces within this rotating bar can become unstable. Stars' orbits can get pulled out of the flat galactic plane, making them oscillate above and below the center. This process, called buckling, causes the bar to thicken and puff up, and as it does, the most stable orbits for stars naturally settle into that distinctive X-shaped pattern. It is a shape born from rhythm and motion, not from a single shattering impact. This discovery quietly revolutionizes our understanding of the Milky Way's past. It suggests our galactic core was built primarily through succession, a slow, internal rearrangement of its own stars, rather than through a dramatic, ancient merger with another large galaxy. That X shape is therefore a cosmic fingerprint, evidence of a specific and graceful dance that our galaxy performed over eons. It tells us the Milky Way is more of a self-made structure, its central form sculpted by the relentless, gentle pull of its own internal gravity. While the boxy bulge reveals the galaxy's gentle internal dance, its very heart is a place of unimaginable violence, a forge that can create the fastest solitary objects ever seen. These are the hypervelocity stars, and they are not merely running away, they are being fired out of the Milky Way like bullets from a cosmic rifle. The current record holder is a star known as S5HVS1, a sun screaming through the halo of our galaxy at a blistering 1,700 kilometers per second. At that speed, it could travel from Earth to the Moon in just over 3.5 minutes. Its trajectory is a perfect, unwavering line, and when astronomers traced its path backward across tens of thousands of light years, it pointed like an accusing finger directly at the galactic center. This was no random ejection from a supernova or a stellar billiard game in a cluster. This star received its unimaginable kick from a single, supreme source, the supermassive black hole Sagittarius A star. The mechanism is a masterpiece of gravitational physics called the Hill's mechanism. Picture a binary star system, two stars orbiting each other, drifting too close to the sleeping giant at the galaxy's core. The immense tidal forces from the black hole can violently tear the binary apart. One star gets captured into a tight, doomed orbit around Sagittarius A star, while its companion is flung away with the combined orbital energy of the entire system, catapulted into the abyss at a significant fraction of the speed of light. S5HVS1 is that flung companion, a solitary survivor of a stellar marriage ripped apart by the ultimate gravitational predator. This star is more than just a speed demon. It is a pristine probe, a messenger from a region we cannot directly observe. As it races outward, its composition, its speed, and its trajectory carry encoded information about the environment right next to the black hole. By studying it, we can infer conditions in that chaotic realm, measuring the sorts of binary systems that wander there and the ferocious power of the tides they encounter. Each hypervelocity star we discover is a fossilized record of a singular, catastrophic event at the galactic core. Their existence confirms that Sagittarius A star, though quiet now, is an active and brutal sculptor of our galaxy's population, capable of hurling entire suns into the endless dark between galaxies. The ultimate fate of these stars is a profound loneliness. They carry too much speed to ever be recaptured by the Milky Way's gravity. They will cross the galactic frontier and sail out into the intergalactic void, where they will shine as isolated beacons for eternity, their light a permanent testament to the day they survived an encounter with the monster at the heart of everything. Those hypervelocity stars are cosmic exiles, flung from the galactic core into the void, but some of the most violent and creative places in the universe choose to stay put, burning with a ferocious green light. Far beyond the Milky Way, astronomers hunting through public telescope data made a charming discovery: the green P galaxies. These are small, compact galaxies that appear as tiny, fuzzy green dots in digital sky surveys. Their color is not a trick of the light, it is a vital sign of cosmic trauma and creation. The intense green hue comes from a specific, powerful emission line of doubly ionized oxygen, a fingerprint of gas that has been blasted by an extraordinary amount of ultraviolet radiation. This radiation can only come from a staggering frenzy of newborn, massive stars. A green P galaxy is essentially one gigantic, chaotic stellar nursery, a place where star formation is occurring at a rate hundreds of times faster than in our own Milky Way relative to its size. It is a galaxy-wide firestorm of birth, so intense it lights up the surrounding gas in this unmistakable neon green glow. These objects are typically found billions of light years away, snapshots of the early universe when such frantic construction was common. But this raises a compelling question. Does our own, more mature Milky Way contain any regions that mimic this extreme, green-tinged violence? While we lack an entire galaxy undergoing such a frenzy, we do possess spectacular local analogues, cosmic laboratories where we can study the physics of extreme starbirth up close. The prime candidate is not within our main galactic disk, but in a satellite galaxy we orbit, the Large Magellanic Cloud. There, you will find the Tarantula Nebula, also known as 30 Doradus. This is not a gentle cloud of gas. It is the most active star-forming region in our entire local group of galaxies. If placed at the distance of the Orion Nebula, the tarantula would cast shadows on Earth and be visible as a colossal cloud covering a quarter of the sky. At its heart lies a dense cluster of titanic stars, including R13601, one of the most massive and luminous stars ever recorded. The ultraviolet radiation pouring from these stellar infants is so fierce it ionizes the surrounding hydrogen gas, causing the entire nebula to glow with a pinkish-red hue. But crucially, embedded within that glow are the same strong oxygen emission lines that give the distant green peas their color. The tarantula is, in essence, a green pea in miniature, a concentrated knot of the same violent stellar genesis. Studying it allows astronomers to dissect the process in real time. We can see the massive stars themselves, watch how their winds carve cavities in the gas, and observe the triggered formation of subsequent star generations. It is a detailed blueprint for the chaos that defines those distant green dots. So, while our Milky Way may not host a galaxy-wide starburst, it keeps a furious, green-hearted cousin in its cosmic backyard, a nearby window into the universe's most fertile and violent creative act. The furious green glow of stellar birth is a temporary blaze, but the final acts of massive stars leave behind phantoms on a far grander scale. Drifting across the constellations of Vela and Puppis is a cosmic ghost so vast it defies comprehension, the Gum Nebula. This is not a sharp, glowing cloud like the Orion Nebula. It is a faint, reddish veil of hydrogen gas that spans an incredible 40 degrees of the southern sky. To put that in perspective, if you held your arm outstretched and made a fist, the Gum Nebula would cover the area of 80 fists placed side by side. It is an ancient fading star, the remnant of a supernova, or perhaps a series of them, that detonated over 1 million years ago. The star that created it died long before humans walked the Earth, but its final breath still surrounds us. In fact, our solar system is likely drifting within the nebula's outermost, most tenuous layers. We are inside the ghost, making it extraordinarily difficult to see its full structure, like trying to map a fog bank from deep within the fog. At the heart of this immense cloud lies the powerhouse that keeps it glowing, the Vela pulsar. This is the ultra-dense, spinning corpse of the star that exploded, a neutron star rotating 11 times every second. It beams out intense radiation and particles, a cosmic lighthouse whose energy continuously excites the surrounding gas, causing the entire nebula to emit its faint, red hydrogen alpha glow. The Gum Nebula represents the ultimate fading echo. It is the aftermath of a stellar catastrophe so immense that, even after 1 million years of expansion and dilution, its debris still fills a significant portion of our local galactic neighborhood. It is a reminder that the space between the stars is not empty. It is a graveyard and a recycling center filled with the slowly dispersing remains of ancient giants. We are literally breathing space that was once part of a star, living inside the lingering memory of its violent death. This ancient, fading echo of the Gum Nebula surrounds us, but our galaxy's influence stretches far beyond its glowing spiral arms. It commands a court of smaller, orbiting galaxies, and here we find a structural oddity that challenges cosmology itself. The Milky Way is not alone. Dozens of dwarf satellite galaxies, like the Large and Small Magellanic Clouds, circle it like moons around a planet. According to our most successful model of the universe, called lambda cold dark matter, these satellites should be scattered around us in a roughly spherical swarm. They should orbit in all directions, some going clockwise, others counterclockwise, like bees buzzing around a hive. But the reality astronomers observe is starkly different. A significant number of these dwarf galaxies are not scattered randomly. Instead, they are aligned in a startlingly thin, rotating plane. It is as if someone took a giant, invisible dinner plate and placed it edge on around the Milky Way, then glued most of the satellites onto that plate. They orbit together, a coordinated flock of cosmic birds flying in formation, a configuration that appears far too neat and structured to be random chance. This is the satellite disk problem, and it is a profound headache for theorists. The lambda cold dark matter model, which beautifully explains the large-scale structure of the entire cosmos, predicts that small galaxies should fall into larger ones from all directions over time, guided by the invisible filaments of dark matter. They should not arrive in a single, synchronized group moving in the same plane. So how did this thin disk form? One compelling explanation is that these satellites did not arrive individually. They may have fallen into the Milky Way's grasp as a group, perhaps as remnants of a single, larger galaxy that was torn apart billions of years ago. Their shared motion today would simply be the fossilized trajectory of that ancient capture event, a galactic train that never fully derailed. This idea has gained traction with the discovery of similar planes of satellites around our neighbor, the Andromeda Galaxy, suggesting such group infall might be a common, if unexpected, feature of galactic growth. But the alternative explanation is far more revolutionary. Perhaps this strange disk is not a quirk of history, but a sign that our understanding of the fundamental rules is incomplete. The Standard Model relies heavily on the properties of dark matter being cold and collisionless, meaning its particles interact only through gravity, not by bumping into each other. This allows dark matter to form diffuse, spherical halos around galaxies. But if the satellite disk is truly a stable, long-lived structure, it might imply that dark matter has more complex properties. Could it interact with itself in ways we have not accounted for? Or could the gravitational forces at these scales work differently than our equations predict? The thin, rotating plane of satellites is more than just an orbital curiosity. It is a cosmic arrangement that should not exist according to the textbooks, a structural ghost in the machine of our best theories. It forces astronomers to question whether they are seeing the aftermath of a singular, violent event in the Milky Way's past, or the first visible cracks in our model of the universe's hidden skeleton. Each tiny, faint dwarf galaxy in that disk is not just a satellite, it is a silent witness, and its path holds a secret that could reshape cosmology. That thin disk of orbiting dwarf galaxies may be a ghost from the Milky Way's past, but another ghost is returning home. Racing toward the spiral disk from the desolate galactic halo is a colossal, silent specter known as the Smith Cloud. This is not a cloud of water vapor, but a titanic river of atomic hydrogen gas, a structure so vast it contains enough material to forge over 2 million stars the size of our sun. Discovered in the 1960s by astronomy student Gail Smith, its true nature remained a mystery for decades. It appeared as a faint, fast-moving smudge on radio telescope maps, a dark ship sailing through the void. For years, the leading theory was that it was a pristine, intergalactic cloud, a virgin lump of primordial gas falling into the Milky Way for the first time. But the truth, revealed by detailed observations from instruments like the Hubble Space Telescope, is far more poetic. The Smith Cloud is not a stranger. It is a piece of our own galaxy coming back. Spectroscopic analysis revealed its chemical fingerprint. The cloud is enriched with sulfur, a heavier element forged in the hearts of massive stars. This sulfur abundance matches the outer regions of our galaxy's disk. The evidence is clear. The Smith Cloud originated from within the Milky Way itself. Somehow, about 70 million years ago, a titanic event, perhaps the shock wave from a cluster of supernova or a close gravitational encounter, blasted this enormous parcel of star-forming gas clear out of the galactic plane. It was flung into the halo, a piece of the galaxy violently ejected, and now, like a cosmic boomerang, it is falling back. Its trajectory is a slow-motion collision course. The cloud is moving at nearly 300 kilometers per second and is currently about 8,000 light-years from the disk. In roughly 30 million years, it will plow directly into one of our galaxy's spiral arms. The impact will be a spectacle of pure cosmic creation. When that much cold, dense gas slams into the even denser material of the galactic disk, it will create immense shock waves. These shock waves will compress vast regions of gas, triggering gravitational collapse on a colossal scale. the result will be a brilliant firestorm of new star formation, a stellar baby boom lighting up that region of the Milky Way for millions of years. The Smith cloud is a reminder that galaxies are not closed systems. They can belch out their own material, only to recapture it eons later in an act of regenerative violence. We are witnessing a single thread in the galactic recycling process, a piece of the Milky Way that went on a long journey into the darkness and is now returning to seed its future. That returning cloud is a testament to our galaxy's dynamic past, but its ultimate fate is to feed the single most dominant presence in the Milky Way. At the very center of everything, a gravitational monster sleeps. Sagittarius, a star, is the supermassive black hole anchoring our galaxy, a cosmic singularity with a mass 4 million times that of our Sun compressed into a space smaller than the orbit of Mercury. Yet for all its power, it is strangely, profoundly quiet. Unlike the brilliant quasars that blaze in distant galaxies, our central black hole is a dormant giant, emitting only faint whispers of radiation. This quietude is our first great mystery. Why is our galactic heart so still? The answer likely lies in its diet. A black hole only shines brightly when it is actively feeding, when vast quantities of gas and dust spiral into its accretion disk, heating to millions of degrees before vanishing beyond the event horizon. Currently, Sagittarius, a star, exists in a relative famine. The region around it is swept relatively clean of material, leaving the beast with only occasional small snacks. This quiet allows us to observe the extreme environment right at its doorstep with unprecedented clarity, and what we see there defies simple explanation. Take the bizarre G objects. These are strange, dusty blobs orbiting perilously close to the black hole. They look like compact clouds of gas, but they move with the precise, fast orbits of stars. The leading theory is that they are, in fact, stars, but stars that have been cloaked in thick veils of gas and dust, perhaps puffed out by the black hole's fierce tidal forces during close encounters. They behave like cosmic matryoshka dolls, hiding a stellar core inside a gaseous envelope, a structure that should be ripped apart by the black hole's gravity, yet somehow persists. Then there are the stars themselves, like the famous S2, which whips around the black hole in a blistering 16-year orbit, reaching speeds of over 25 million kilometers per hour at its closest approach. These stellar trajectories are the ultimate test of Einstein's theory of general relativity, their orbits precessing in a way that Newtonian gravity cannot explain, tracing a rosette pattern in the void. In 2019, we were granted our first direct visual evidence of the shadow of this behemoth. The Event Horizon Telescope Collaboration, a global network of radio telescopes functioning as one Earth-sized instrument, produced an image of the glowing ring of superheated gas swirling around Sagittarius, a star's event horizon. That iconic orange donut is not the black hole itself, but the light from its final, doomed orbital path, outlining the point of no return. Yet the image raised as many questions as it answered. Why is the ring slightly lopsided? What causes the bright knots within it? How does the magnetic field around the black hole shape the flow of matter? Perhaps the deepest mystery of all is how Sagittarius, a star, came to be. Did it grow slowly over billions of years by swallowing gas and merging with smaller black holes? Or did it form directly from the collapse of a gigantic primordial gas cloud in the early universe? Its presence and its quiet influence are fundamental to the Milky Way's very existence. The energy from its long-past feeding frenzies may have helped shape the galactic bulge and regulate star formation across the entire galaxy. It is the silent, invisible pivot around which our entire cosmic home rotates, a sleeping giant whose dreams dictate the fate of 200 billion stars. Even the silent giant at the center must contend with the ghosts of its past meals. Wrapping around the outer fringes of the Milky Way, far beyond the familiar spiral arms, lies a faint, celestial river known as the Monoceros Ring. This is a vast, looping stream of ancient stars, a gossamer structure so immense it nearly encircles our entire galaxy. For years after its discovery, this ring was considered a stunning archaeological find, the clearest evidence of galactic cannibalism in action. The prevailing theory was elegant and violent. A small dwarf galaxy, perhaps similar to the Sagittarius dwarf spheroidal that is currently being torn apart, ventured too close to the Milky Way billions of years ago. Our galaxy's immense tidal forces, the difference in gravity between the near and far side of the intruder, slowly shredded it. The stars of that doomed galaxy were not swallowed all at once. Instead, they were pulled out into long, looping streams that orbit the Milky Way, like sugar dissolving and spiraling in a cup of coffee. The Monoceros ring, according to this view, is the largest and most prominent of these stellar rivers, the final, fading signature of a galaxy that was eaten alive. This narrative fits perfectly with our understanding of how large galaxies grow. They are cosmic predators, absorbing smaller neighbors to gain mass and stars, and the Monoceros ring would be the fossilized remains of one such ancient feast. Yet, as astronomers measured the ring's properties with greater precision, a troubling complication emerged. The stars within the Monoceros ring are not just old. Their chemical composition, their metallicity, is surprisingly high. They contain a significant amount of elements heavier than hydrogen and helium, elements that are forged in the hearts of stars and scattered by supernova. This is a problem. Small, ancient dwarf galaxies are typically metal-poor, composed of pristine, early universe material. The stars in the Monoceros ring, however, look suspiciously like stars from the Milky Way's own outer disk. This led to a radical counter-theory. Perhaps the ring is not a captured alien stream at all. Maybe it is us. The Milky Way's disk is not a perfectly flat, rigid plate. Its outer regions are flared and warped, likely from gravitational interactions with passing satellite galaxies or dark matter clumps. Some astronomers argue that the Monoceros ring is simply the most extreme manifestation of this warp. In this scenario, the ring stars were born right here in the Milky Way, in the far-flung outer disk. Gravitational perturbations then pulled this entire section of the disk upward, bending it into a vast, ring-like structure that we now see projected against the halo. It would be a colossal ripple in the fabric of our galaxy, a permanent wave frozen in starlight. The debate between these two ideas, the cannibalized dwarf versus the warped disk, remains fierce and unresolved. Each side points to compelling evidence. Proponents of the accretion model note the ring's coherent motion and its alignment with other known streams. Supporters of the warp model highlight the troublesome chemical similarity to our disk stars and the sheer difficulty of getting a disrupted dwarf galaxy to form such a smooth, giant ring. This controversy makes the Monoceros ring one of the most important and strange features in our galactic halo. It is a cosmic Rorschach test. Depending on your interpretation, it is either a ghost of a vanquished neighbor or a reflection of our own galaxy's twisted anatomy. Until we can trace the orbits of its individual stars with even greater fidelity, this faint loop of suns will remain a beautiful enigma, a reminder that sometimes the most familiar things, when viewed from a great distance, can become utterly strange. This galactic asymmetry extends to a quieter, more puzzling neighborhood. Look toward the constellations of Vela and Carina, and you are peering into the third galactic quadrant. Here, astronomers have mapped a curious void. This region of our spiral disk, between 180 and 270 degrees in galactic longitude, is strangely sparse. It holds a surprising dearth of the massive, brilliant O-type stars and the sparkling young open clusters that typically light up other sectors of the Milky Way. It is not a true emptiness like the Boötes void, but within the bustling stellar city of our galaxy, this quadrant feels like a quiet, underdeveloped suburb. While other spiral arms blaze with stellar nurseries, this area appears to be a cosmic desert, a place where the frenetic business of star formation has slowed to a whisper. The question is why? What makes this particular slice of our galaxy so different? One compelling clue lies in the architecture of the spiral arms themselves. Our galaxy is a barred spiral, and its arms are not solid structures but density waves, like traffic jams moving through a stream of stars and gas. The pattern of these waves dictates where gas clouds pile up, compress, and collapse to form new stars. In the third quadrant, the layout of these arms may create a kind of gap or a less pronounced wave crest. Imagine a musical rhythm where the beat is strong in 3 measures but faint in the 4th. This region might simply occupy the faint part of the pattern, where the gravitational nudge that triggers star formation is significantly weaker, leaving the gas too diffuse and quiet to birth many massive stars. Another, more dramatic possibility involves the galaxy's violent history. This quadrant's quietude could be the lingering scar of a past gravitational encounter. A close pass by a satellite galaxy, or even the ancient shockwave from a nearby supernova bubble on a galactic scale, might have swept through this area millions of years ago. Such an event could have done 2 things. It might have compressed gas in other regions, triggering star formation there, while simultaneously pushing the gas in this quadrant outward, dispersing it and effectively sterilizing the zone for future generations of stars. It would be like a cosmic wind blowing the fertile topsoil from one field to another, leaving behind barren ground. This creates a fascinating paradox. We think of our galaxy as a roughly symmetrical pinwheel, but the distribution of its youngest, brightest citizens tells a different story. It reveals a lopsidedness, a patchiness in its creative potential. The empty quadrant is a reminder that the Milky Way's evolution is not a uniform process. It is a mosaic of different environments shaped by the invisible architecture of spiral density waves and the echoing ghosts of ancient disturbances. This quiet desert within our star-rich city challenges the simple picture of a harmonious spiral, showing us that even galaxies can have their forgotten corners and fallow fields. That quiet desert in our galaxy's spiral arms is defined by what is missing, but some of the most profound searches are for particles that should not be there at all. High above the Earth, carried by the winds, scientific balloons have floated detectors into the thin upper atmosphere, hunting for cosmic rays, the atomic shrapnel flung across space by violent events. Within this rain of ordinary particles, a few experiments have reported an electrifying anomaly, a handful of signals that look exactly like the nuclei of antihelium. This is the chemiok and antimatter signal, a whisper of something profoundly unnatural. Antimatter is the mirror image of normal matter. For every particle, like a proton or an electron, there is an antiparticle with opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy. According to our standard models, antimatter should be exceedingly rare in the cosmos today. The Big Bang should have created equal amounts of matter and antimatter, and their mutual annihilation should have left behind almost nothing. The fact that we and our galaxy exist at all is one of physics' greatest mysteries. Finding complex antimatter nuclei like antihelium floating freely through the Milky Way would be revolutionary. It would mean that somewhere out there, processes are actively creating and preserving antimatter in bulk, building anti-atoms into anti-nuclei. The detection is fiendishly difficult. These balloon-borne instruments must sift through billions of ordinary cosmic ray protons and helium nuclei to find a single candidate antihelium event, a needle in a cosmic haystack where the hay is constantly moving at near light speed. The few tentative detections reported over the years are thus treated with extreme caution, as a single misidentification from a complex particle collision within the detector itself could mimic the signal. But if it is real, where could it come from? One thrilling possibility points back to the galaxy's dark side. If dark matter is composed of certain types of particles, they could be colliding and annihilating within dense regions of the Milky Way's halo. Such annihilations could, in theory, produce showers of particles and antiparticles, including the building blocks of antihelium. This would be a direct, tangible signal from the invisible stuff that shapes the universe. Alternatively, the source could be an exotic astrophysical factory, perhaps an ultra-dense object like a neutron star collision or a special type of supernova could forge antimatter nuclei in its furious aftermath and accelerate them into space. There is even the remote, staggering possibility of an entire region of the galaxy, or a distant antimatter star where the normal rules of composition are inverted. Confirming even a single, unambiguous antihelium nucleus from space would send shockwaves through physics and cosmology. It would force a rewrite of our understanding of both the large-scale structure of the universe and the fundamental laws of particle interactions. It is a search for a ghost that should not exist, a potential clue that our galaxy is not just home to strange objects, but to an entirely alien form of substance hiding in plain sight. While the colossal Fermi bubbles dominate the view, our galaxy's core is not venting its energy through a single pair of lungs. It breathes through a network of smaller, intricate passages. These are the galactic geysers, a complex ecosystem of energetic outflows that reveal the dynamic atmosphere of the Milky Way. If the Fermi bubbles are the titanic exhalation from a past cataclysm, these structures are the steady, ongoing steam vents from a perpetually active kitchen. They appear in different wavelengths of light, each telling a different part of the story. In microwave light, the Planck satellite mapped a mysterious diffuse glow, often called the microwave haze, a fog of energetic particles that fills the same central region but with a finer, more filamentary structure. Then, in X-ray vision, the Chandra and XMM Newton observatories have spotted towering chimneys of superheated gas. These chimneys seem to connect the bustling stellar factories at the very center directly to the base of the massive Fermi bubbles high above. Think of it like this: the galactic center is a dense, vibrant metropolis, a forge where stars are born and die in rapid succession. This forge produces immense waste heat and fast-moving particles, the exhaust of a billion stellar engines. The galactic geysers are the city's ventilation shafts. They channel that hot, processed exhaust upward, away from the crowded streets of the spiral disk and into the thinner air of the galactic halo. This isn't just waste disposal, it's a crucial part of galactic ecology. These outflows carry chemically enriched material, heavy elements forged in supernova, and fling them far out into the galaxy's surroundings. This process, called galactic feedback, is a fundamental regulator. By venting this energy and matter, the geysers actually help control the rate of star formation in the central regions. They can blow away the very gas clouds that would otherwise collapse to form new stars, preventing the core from burning itself out in a single, unsustainable frenzy. So these structures are more than just pretty lights in different colors. They are the pressure release valves for the Milky Way's most energetic district, the pathways that distribute the products of stellar life and death throughout our galactic atmosphere, slowly and steadily shaping the environment in which all future stars, including our own sun, will be born. The galactic center's intricate venting system shows a galaxy in constant conversation with itself. But what if the Milky Way holds entire conversations in the dark? This leads us to one of the most profound and controversial ideas in modern astronomy, the concept of a dark galaxy. Imagine a clump of matter with the mass of a small galaxy, perhaps billions of times the mass of our sun, drifting through space. Yet when you point any telescope at it, you see almost nothing. No glittering spiral arms, no brilliant clusters of stars, just an apparent emptiness. This is the hypothetical dark galaxy, a structure made almost entirely of dark matter and perhaps a whisper of hydrogen gas, but with so few stars it is essentially invisible. It would be a ghost of a galaxy, a cosmic framework without the finished building, and finding one would revolutionize our understanding of how galaxies form. The most famous candidate for such an object is known as Virgohi-21, discovered in the Virgo cluster. Astronomers detected a cloud of neutral hydrogen gas through its radio emissions, but when they looked with optical telescopes at the same spot, they found no stars to account for it. More intriguingly, the gas cloud appeared to be rotating. The speed of that rotation suggested the cloud was held together by a gravitational force far greater than the visible gas alone could provide. The simplest explanation was that the hydrogen was embedded in a massive halo of dark matter, a halo with the gravitational pull of a small galaxy but without the stars to light it up. It was as if they had found the spinning rim of a wheel, but the wheel itself was made of invisible stuff. The discovery sparked immediate and fierce debate. Skeptics proposed other explanations. Could Virgohi-21 simply be a tidal tail, a stream of gas pulled from a known galaxy during a close encounter? Perhaps it is a failed galaxy, a cloud of gas that was simply too diffuse or too violently disturbed to ever coalesce into stars. The debate rages because the stakes are so high. If dark galaxies are real, they would be the purest natural laboratories for studying dark matter we could ever hope to find. Within them, the mysterious substance would exist in near isolation, its gravitational effects unmasked by the complicating glare and complex physics of billions of stars. We could map its distribution with precision by tracing the motion of the scant hydrogen gas, learning how it clumps and behaves on the scale of an entire galactic halo. Their existence would also answer a deep question about galaxy formation. Our current models suggest there should be far more small, dwarf galaxies orbiting large ones like the Milky Way than we actually see. This is known as the missing satellites problem. Could it be that many of these missing satellites are not missing at all, but are simply dark, starless halos that our telescopes have overlooked? The hunt is now on within our own galactic neighborhood. Could the Milky Way host such a dark satellite, a silent, massive companion we have yet to detect? Surveys scan the skies for faint, unexplained clouds of hydrogen gas with peculiar motions, any hint of a massive ghost passing through our starry realm. Finding one would be like discovering that our familiar cosmic home has a silent, unseen twin, a shadowy sibling made of the universe's most secret substance orbiting us all along. These galactic geysers and dark matter ghosts are not the only strange threads woven into the Milky Way's core. Hundreds of mysterious filaments hang in space there, each a perfectly straight, magnetized line stretching for tens of light years. They look like cosmic hairs combed outward from the central black hole, or perhaps like the strings of a vast, invisible harp. We only see them at all because they glow faintly in radio waves, a specific frequency that reveals their true nature. They are not made of gas or stars, but of electrons spiraling at near light speed through powerful magnetic fields, a process that emits this telltale radio hum. Their arrangement is what makes them so utterly perplexing. They are not scattered randomly. Instead, they are organized with an eerie precision, aligned perpendicular to the flat plane of the galaxy itself. They stand on end like giant needles radiating from a central point near Sagittarius, a star, creating a bristling, spherical halo of lines around the black hole. This organized defiance of the galactic disk's orientation is a clear clue that something extraordinary is at work. The leading theory connects them directly to the sleeping giant's past outbursts. Imagine the powerful jets and outflows that once inflated the colossal Fermi Bubbles. As those titanic winds blew outward from the galactic center, they would have dragged and stretched the Milky Way's own magnetic field lines with them. According to this idea, the filaments are fossilized remnants of that process. They could be like cosmic wake lines, trails of magnetic force left behind as the outflowing material plowed through the interstellar medium, accelerating electrons to incredible speeds along these specific paths. In this scenario, each filament is a frozen snapshot of magnetic energy, a relic of a time when the black hole was violently active. Yet even this elegant explanation faces difficult questions. Why are the filaments so numerous? Why are they so remarkably uniform in length and thickness? And what physical process keeps the electrons energized and spiraling along these specific tracks for millions of years, long after the initial outburst has faded? Some astronomers wonder if they are not passive relics but active structures, perhaps continuously re-energized by shocks or turbulence in the chaotic central environment. Their exact origin and nature remains one of the most enduring and beautiful puzzles of the galactic center. They are a stark reminder that even in the domain of a supermassive black hole where gravity reigns supreme, magnetism can weave structures of stunning order and longevity, creating a permanent, radiant lattice in the heart of chaos. Those magnetic filaments are a permanent monument to the galactic center's violent past, but our galaxy's history is written in the very motion of its stars. A ghost walks among us, a phantom structure woven from the paths of millions of ancient suns. It is called the Gaia sausage, or sometimes Gaia Enceladus, and it is the fossilized imprint of the most catastrophic event in the Milky Way's life. The story of its discovery begins with a map, the most precise three-dimensional chart of our galaxy ever created by the European Space Agency's Gaia spacecraft. Gaia did not just plot where stars are, it precisely measured how they move. When scientists began analyzing the velocities of millions of stars, a shocking pattern emerged in the data. A vast population of ancient stars was not moving in the orderly, circular orbits typical of the galactic disk. Instead, their paths were highly elongated, plunging in on radial, egg-shaped orbits that brought them screaming close to the galactic center before swinging far out into the halo. When you plot these specific stars by their speed toward or away from the galactic center versus their sideways motion, the data points cluster into a distinct shape, a dense, plump oval that astronomers immediately nicknamed the sausage. This was not a random distribution. It was the clear signature of a single, coherent structure, a flock of stars all moving together with a shared history. That shared history is one of destruction and assimilation. The Gaia sausage is the scattered remains of a dwarf galaxy, perhaps 1/4 the mass of the early Milky Way that ventured too close some 10 billion years ago. It did not simply pass by. It collided head-on in a merger of staggering violence, a slow-motion crash that would have reshaped the cosmos around our young sun. The smaller galaxy was utterly torn apart by the Milky Way's gravity. Its stars were not absorbed neatly. They were strewn across chaotic, plunging orbits, their once orderly motion scrambled into the radial paths we see today. This ancient cataclysm did far more than just add stars to the halo. It likely forged the Milky Way as we know it. The immense gravitational shock of the collision would have violently stirred up the gas and stars of the primordial Milky Way, puffing them up to form the galaxy's thick disk, that populated region of older stars that surrounds the thinner, younger disk where our sun resides. It may have also delivered a massive influx of gas, fueling a tremendous burst of star formation. In a very real sense, we are living in the aftermath of this galactic wreck. Many of the ancient stars in our halo, and perhaps even our own sun, may have formed from the turbulent wake of that colossal merger. The Gaia sausage is therefore more than a strange object. It is our galaxy's birth certificate and a record of its most defining trauma. It transforms the Milky Way from a static island in space into a dynamic entity with a vivid, violent biography. We are not just inhabitants of a spiral galaxy. We are the descendants of a cosmic collision, living in a structure built from the ruins of another world. That galactic biography written in starlight is mirrored by a chemical fingerprint written in infrared light, a signature so common it is painted across the entire galaxy. As we conclude our journey, we arrive not at a single spectacular object, but at a molecular whisper, a set of mysterious emissions known as the unidentified infrared bands. In the dark, frigid clouds between the stars, where temperatures hover just above absolute zero, a strange glow persists. When astronomers point infrared telescopes at these regions, they detect not a smooth spectrum, but a series of sharp, specific spikes at certain wavelengths. It is as if the darkness itself is humming a distinct, complex chemical tune, and this same tune is heard everywhere, from the heart of brilliant nebulae to the quiet, cold voids of interstellar space. These bands are the calling card of something substantial, something organic. The leading suspect is a family of large, sturdy molecules known as polycyclic aromatic hydrocarbons. Imagine the soot from a candle flame not as simple black carbon, but as intricate, microscopic snowflakes made of interlocked rings of carbon and hydrogen atoms. These PAHs are thought to be incredibly resilient, able to survive the harsh radiation of space, and when they are gently warmed by starlight, they vibrate and emit these very specific infrared frequencies. Yet, for all their promise, their exact identity remains frustratingly uncertain. The infrared bands we see are a blurry composite, a chorus of millions of slightly different molecular variations all singing similar notes. Pinpointing the precise molecules responsible is like trying to identify every instrument in a symphony by listening from outside the concert hall. This chemical mystery is profoundly important because these molecules are everywhere. They are the most abundant complex organic molecules known in space, a ubiquitous soot tracing the contours of our galaxy's anatomy. Wherever new stars are being born, lighting up vast clouds of gas and dust, these infrared bands shine brightly, outlining the fertile regions of cosmic creation. But their significance runs even deeper. Polycyclic aromatic hydrocarbons are not just cosmic graffiti, they are potential seeds. Their complex, ring-based structure is a stepping stone toward even more complicated chemistry. In the icy mantles of dust grains within nebulae, bathed in starlight and cosmic rays, these PAHs could be processing into the precursors of amino acids and other molecules essential for life. They may be the galaxy's way of scattering the raw chemical ingredients for biology long before planets ever form, a prebiotic drizzle falling across countless solar systems. So the final strange object in our Milky Way is not a place or a star, but a substance, a cryptic signature written in infrared light. It is a reminder that the galaxy is not just a collection of brilliant points and vast structures, but a complex chemical factory, quietly assembling the very pieces that might one day, somewhere, spark the miracle of life itself. From the faint chemical hum of interstellar dust to the colossal echo of ancient galactic collisions, our journey reveals a single truth. The Milky Way is not a serene island of stars. It is a living, breathing, and deeply weird ecosystem. We have wandered through gravitational anomalies like the Great Attractor, an unseen hand pulling entire galaxies. We have stood in the shadow of the Fermi Bubbles, the fossilized breath of a black hole's tantrum. We have chased stellar fugitives like the Cannonball pulsar and puzzled over the perfect geometry of invisible radio circles. Each object, from the dark matter ghost of Virgoh I-21 to the smoky exhalations of ancient red giants, is more than a cosmic curiosity. It is a frontier. Every strange glow, every silent void, every star moving in an impossible way is a question written across the sky, waiting for its answer. These are the pieces of a puzzle we are only beginning to assemble, clues to the forces that built our galactic home and that will dictate its future. So the next time you gaze up at that familiar Milky Band arching overhead, remember what it truly contains. It is a vault of ghosts and monsters, a graveyard of giants, a nursery for worlds, and a laboratory for the laws of physics themselves. Our cosmic neighborhood is far stranger, more violent, and more wonderful than we ever dreamed. Look up with that new knowledge, let it fill you with wonder. And if you want to keep exploring these mysteries with us, make sure to subscribe. Tell us in the comments below which of these 25 strange objects captivated you the most. Was it the runaway stars, the dark matter signal, or the ancient galactic sausage? The conversation about our incredible universe is just